about the consensus we usually mean in social science. This is actually about the stability of graph partitions across different runs of the same algorithm on the same data. And this is a very natural problem to be addressed in physics, but it is much more seldom acknowledged and addressed outside physics as a discipline. And so there are many unresolved issues here, particularly in the sphere of clustering and graph partitioning. So I find that this is a very important topic, and I'm sure that we will hear a very exciting presentation. So Santa, the floor is yours.
Thanks a lot, Alessia. Thanks, and nice to see you after a while, you and I see Sergey and others. And thanks also, Dima, for inviting me over Messenger, actually, a few months ago. I didn't know about this event. So can you hear me well?
Yes, we can.
Yeah, so let me share the screen and say a few things about this topic you just announced. So let me also go. Okay, can you see the first slide?
Yes.
Okay, so like Alessia said, somehow, I mean, I spend a lot of time dealing with this topic of finding partitions in graphs. And today's topic is not about a specific algorithm to find those partitions, but it's about checking the stability of partitions. So basically dealing with noise. So let me say a few things. First of all, I mean, I want to acknowledge the collaboration with my PhD student, Aditya Tandon, who is the main driver of this paper that you see. They're going to discuss a bit more in detail in a few minutes. So this is a talk about community structure, which regardless of the discipline you're coming from, is really a transversal topic, because when you want to simplify the structure of a network, you often break it down into pieces, and you want to know how to do it fast and well. And today, of course, I will focus about specific things. So community structure is basically a modular organization of a network, like in a very schematic example that I'm showing here, in which you have somehow, in this case, these three groups of nodes, which are tightly connected to each other, but sparsely connected between each other. So how to find those things and why this is important? This is, based on the numbers, really, the single most popular topic within network science. So most of the highly cited papers in this topic are about that, because it's an important methodology that is it's used in many different domains dealing with networks. So the reason why it's useful or even important to do this operation, so to break the system into pieces, is we want to know how it is organized. It's like identifying the organs in a human body. You want to identify the features of the nodes, because you assume that groups of nodes are indicate that the nodes have similarity, so that they may share some features that can be revealed by the topological organization. You may also classify the nodes based on their position on the classes. Once you have a partition like this one that you see here, you can, within each cluster, distinguish nodes which are somehow fully embedded within their clusters, like the ones, their cluster, which the ones that I'm circling here in red, or nodes which are connected also to nodes of the other classes, so-called gatekeepers, which are the ones that allow you somehow to move from one piece of the systems to another. But it is a difficult problem. It is an ill-defined problem first, which is why so many people are still working on it. It's an unsupervised classification problem. You don't know exactly what you're looking for. You may have ideas. There are different ways to conceptualize it. But there is also an agreement about some of the main guidelines. So basically what we would like to do here, this is the adjacency matrix of this network. Here is 15 by 15. There are 15 nodes here, where the ones indicate that there is a link between nodes with those labels, and empty space much better than zeros, because otherwise this matrix would be dominated by zeros, indicate that there are no links between them. So if you take a look at this matrix, you don't seem to recognize any structure, nothing that can make you think that the system has a model organization, which is clearly displayed by this diagram. But if you rearrange the labels of the nodes here in the order of the modules, putting first the red, then the blue, then the yellow, but you can of course proceed in any order. The very same matrix takes an approximately block diagonal form, which shows you indeed that there are groups of nodes which like each other more than they like the other nodes. So basically, graph clustering or community detection, community discovery means basically going from here to here. And there are many different ways to do it. I'm not going to discuss about the specific ways to do that. I'm going to discuss about the fact that most of these methods, if not all of them, are stochastic in nature, which means basically that they may produce different answers if you change the random seed that you choose to run those algorithms. Because very often you have to choose random numbers when you run a Monte Carlo, when you optimize a function. So, and when we deal with measurement errors, what you have a bunch of measurements, and to make a sense of this collection of measurements, instead of picking one of them, you just make some average and then compute something like, some estimate of the error, I don't know, for instance, variance standard deviation. So this is what you do with numbers. So what happens with partitions? I mean, this is the famous Zachary Karate Club. It's a very well-known social network, small one, 34 nodes, 78 edges, which is being used widely to test clustering algorithms and also for other things. It's a very nice story to tell. This is this club, then it splits in two parts. The two parts are indicated by the squares and the circles here. And the goal is basically to see, is my clustering algorithm good enough to separate the squares from the circles? Is it able to recognize that indeed there are two groups here, even though of course the system is connected? So some of them can do it. Actually, many methods now can do this work very well. But you see, I just apply here InfoMap, which is a very, very well-known algorithm introduced in 2008 by Roswell and Bergstrom. I run it once, I get this partition indicated by the color in 3 groups. I run it again, and I get this other partition in 4 groups. So which one shall I pick? How can I somehow make sense of this slightly different results? So sometimes it can also be very different. This is a small system, so you have also less entropy, right? Less variability in the possible outcomes. But if you have a much larger system, you can also see more differences. So, oh, sorry. So this is what we're going to do here. So how do you basically average partitions? Many methods, like many clustering methods, are stochastic, so they're non-deterministic. You run it multiple times. You may also end up getting often the same answer, but you will also get some answers which are not aligned with the main answer. And of course, this seems to be some kind of strange questions I'm asking, even ill-defined question within an ill-defined problem, because many methods which are stochastic are based on the optimization of a quality function. So if I have a bunch of partitions, I have a number attached to that, which is the value of the quality function for the specific partition. So if I believe my method, I should just get the one with the largest value of the score. So even if I get many answers for my method, in principle, there is an ideal solution or a best solution, which is the one with the largest score. So in a sense, it means that this all premise that I'm making about averaging partition is kind of senseless, because in many cases, I do have a way to single out a partition from this ensemble of results that I get based on the score of the quality function attached to the partition. Not all methods work like that, but in many methods, the most popular ones do, including InfoMap that I just mentioned earlier. What I'm going to show you here is that you can actually use also the suboptimal partitions that you can get by running the procedure multiple times on the same data set, and obtain actually more precise, more robust results by doing that. This is an idea that dates back to a paper in 2002 by computer scientists, as you see, Journal of Machine Learning Research, Strel and Ghosh. It was originally introduced for data clustering, so clustering of objects or data points. But it's a thing, it deals with partitions. So of course, as long as you have partition, it doesn't really matter if it's partition of points, of items, generic items of nodes of the graph, is the same thing. So the idea is searching for the partition which is the most similar on average to the input partition. This is called median or consensus partition. So you have a bunch of partitions, so divisions of your network into groups, and you find this median partition. It's a well, I mean, once you define what similarity means, how to compute the similarity between two partitions, which you can do with standard measures like normalized mutual information, variation of information, and others. This is a very well-defined problem because you have a measure and you explore the space of partition and you find the one which is most similar, which has the largest average similarity with each of the input partitions. However, it is a difficult combinatorial optimization task. The space of partitions grow faster than exponentially with the number of nodes. So it's not obvious how to do this exploration in a precise way. So, but you can, of course, use approximations. And the approximation that has been used most often, it's the one that I'm going to use and introduce to you later, I mean soon in fact, is a greedy solution that adopts what is called a consensus or co-clustering matrix. I'll be calling it mostly consensus matrix, but co-occurrence, co-clustering, consensus, again, given how many different communities deal with clustering, often you may find that the same thing is called in many different ways, across communities. So I'm going to call it consensus matrix. How does that work? The consensus what is a consensus matrix first? So the consensus matrix is a matrix whose entry dij tells you the frequency that the nodes I and j are in the same cluster in the input partition. So you have, say, 100 input partitions, and you check in each of them if I and j are in the same cluster or not. If they are in the same cluster, you mark 1 if you want. If you're not, you mark 0. Then you sum all the ones, you divide by 100 in this case, because you have 100 partitions. So this is a consensus. So basically it tells you how frequently, what is the probability that two nodes are in the same cluster in those input partitions. And this is the basic idea underlying the procedure that we presented in 2012, in fact, and we refined last year in this paper that I introduced at the beginning of the presentation, is that you find the cluster. So basically, once you have a consensus matrix, you consider this as a network matrix. So as a new network, if you want. Of course, it's weighted because the elements are numbers between 0 and 1, this frequency that I mentioned. But a lot of methods can be applied also on weighted graphs very easily. So you cluster the new matrix, you get another set of input partition for the next step of the iteration of the routine. You combine those partitions in a new consensus matrix, and you repeat the procedures until the final consensus matrix you find is block diagonal. Basically, it is composed of disconnected cliques, indicating basically that you end up with the same set of partition. At the end, you have a set of partition which are all identical. So this is procedure which is guaranteed to converge. You always get to that result, and that's your result. And then that will be your approximation to the median or consensus partition. So this is the whole idea. So you have a bunch of input partitions, you create a consensus matrix, you apply your method again on the consensus matrix, treating it as a weighted matrix of a network. You get another set of partitions, you create a new consensus matrix, and you do the same thing until basically at the end, all partitions are the same. So this is the main idea I'm going to sell you today. And what I'm going to tell you next is how to do it in practice, how to make it faster, and what kind of results you can get. So this is more detail what we did in that paper in 2012, which is actually very popular now. And a lot of people, especially in network neuroscience, are using that idea. So you start from a network, G, with n nodes and m edges, and you pick a clustering technique. It doesn't even matter which one you take, as long as it can be applied on weighted graphs as well. I mean, weighted or unweighted. So you start from the input partition, you apply your technique A on G and P times, where NP is the number of input partitions you want to find. You usually get different results. You construct your consensus matrix the way I told you. So basically check how many partitions for I and J, for two nodes I and J, in how many partitions these two nodes are in the same cluster. And you divide by NP. Then you, by doing that, of course, you may end up dealing with the progressively denser matrix, which of course, makes calculations slower. So to make this matrix sparse again, you set a threshold, which is pretty much the only parameter of this procedure, tau. and you set to 0 all the elements below the threshold. So now you have a sparse consensus matrix. You treat it as a weighted matrix of a graph, of a weighted graph, and you reapply your technique A again, MP times on that technique. That gives you a new set of partitions. You can construct another consensus matrix following the instructions of point 2 and 3 to sparsify it until you get this block diagonal matrix. This is a simple example that tells you what this thing can do. Very simple. So you have this graph with 7 nodes. You have a natural partition here in a group of 3 and a group of 4, and you have 4 different partitions for that. 2 of them are the appropriate ones. 2 of them seem to be wrong, right? Because there are these new green nodes, which is basically it's a 3 partition. Number 3 is 3 partition. Number 4 is also 3 partition. So they seem to be very noisy compared to the ground truth, if you want, which is this. If you create a consensus matrix out of these 4 by doing that game that I told you, you get this thing here, which is now, as you see, a weighted matrix, as indicated by the thickness of the lines, which tells you, how big the frequency, how often these 2 nodes, for instance, in this case, appear in the same cluster. So you see, for instance, these 2 nodes are always together, are always blue, you see, in all 4 partitions, which means that gives you a frequency, the highest possible frequency of 1, which is this one, and that's why I'm using the thickest line here. Same goes for these 2 nodes, whereas the other ones are not always co-clustered in all input partitions. So we see what happens basically. At the end of this first round, you end up having a weighted graph, which is clearly more modular than the initial one, because now the edges connecting the 2 groups that you're expected to find are much weaker than the other ones. If you repeat the procedure, eventually these 2 things will disappear, and you end up with the 2 different groups in this case. And that's the principle of this whole procedure. So you see, even though there were 2 answers which were correct and 2 answers which were clearly wrong, the procedure still gives you something which enables you to detect the 2 groups more easily than operating on the original graph. So to check if this trick allows you to find clusters more easily than by working on the original graph, we used our benchmark graph, the LFR what is now called the LFR benchmark, that you can find on my website under resources. It was introduced in this paper, which is super cited now. You see it here, a figure representing the benchmark. It's basically an artificial network with built-in communities. So in which you know basically which are the objects that you have to find. As you can see here, they're indicated by the colors. And the characteristic of this benchmark is that it's meant to be more realistic than the benchmarks that people have been using before we introduced this one, in that clusters have different sizes and nodes have different degrees. In fact, they are both power law distributed. So you see from the size of the nodes, which is proportional to the number of neighbors, to their degree, that there is a broad distribution in both things. And also you see there are small groups, there are large groups. This is more a proxy of what you could think a real networks look like. So then there is a mixing parameter mu, which tells you how blended these different pieces are. If they are well separated, mu is low. If they are kind of mixed with each other, very, very mixed, so harder to find, mu is large, and mu goes between 0 and 1. So when mu is close to 0, these groups are very well separated and very easy to find for most algorithms. When mu starts to approach 1, then everything is mixed and it's going to be different. At some point, there are no classes anymore, so no good methods can realistically find them. So we use this thing, and we produce diagrams like this one. So mu, this parameter that tells you how separated the clusters are, is on the x-axis. On the y-axis, you have the score that tells you how similar your result is to the planned partition, to the natural partition of the system. So we're using normalized mutual information for that. When it is 1, it means that the partitions are exactly identical. When it is close to 0, it means that they are very different. They are basically, you don't do no better than random, like comparing to random partitions. So obviously what happens, as I said, when mu is low, here, for instance, this is Louvain, the Louvain algorithm that now a lot of people are using. Each panel here corresponds to different algorithm indicated by the label propagation method, simulated annealing, still modularity optimization like Louvain is based on the optimization of the same quality function. And also this method is based on the optimization, is a grid optimization of modularity. So these three methods are different ways to optimize the same thing, where this one is an entirely different method. We wanted just to see, how effective this procedure is independently of the specific clustering technique you're using. So you see at the beginning, when mu is close to 0, groups are very well separated, easy to find, and basically what you find is similar, it's pretty much the same thing as you just find the right partition. The two different colors here indicate the original results. So basically what you get if you compare the partitions that you find by applying the method on the graph with the natural partition, whereas the red dots indicate the consensus partition that is found through the procedure I just told you. So as you see, the consensus partition is generally better. I mean, you see the signal, somehow the quality of the performance decay later than the performance of the original algorithm applied directly on the data. This is for 1,000 nodes, this is for 5,000 nodes, and you see nothing really changes. Interestingly, for 5,000 especially, you see here that this method, Cosetta, which is really which is really allows the performance on our benchmarks, you can see by how poor the performance is, it basically goes down right away. These are the black things, the black dots, both for 1,000 and even more for 10,000. You see instead how much better the performance it is once you average the partitions with consensus clustering. So there is a huge gap here. There is even a big gap. So basically here, can you see the difference? That basically in this range of mu, you even find exactly the right partition, even though the method itself is unable to find a good partition. So this is actually the reason why, even though pretty much nobody uses this method anymore, I mean, it helps me to illustrate the potential of this technique. It can really find the signal even when the partitions are very noisy and very far away, I mean, apparently far away from the ground truth. Okay, so basically this is the same exercise we're gonna do. Oh, sorry. Okay, but there is a problem with the initial technique that we proposed in 2012, which is time complexity. If you think about what I told you about how you construct a consensus matrix, if you have a large cluster in one of the input partitions, any pair of nodes in the cluster will give you a score of 1 because they are co-clustered. But that means you have to compute, basically, to consider all pairs of nodes. So if you have clusters which are very large in that partition, which can be the case often, just to compute and to construct the consensus matrix can take you time which is close to n squared, which obviously kills somehow makes the analysis of large networks really problematic, if not impossible. This is the reason why last year we published another paper where we showed how you can alleviate this problem by simplifying the calculation of the consensus matrix. And the trick is that instead of computing the frequency of co-clustering of any two nodes in the network, regardless of whether they are connected or not, you just focus only on the pairs of nodes which are connected, pairs of neighbors. And since you usually deal with a sparse matrix, there are not many pairs of neighbors with respect to all possible pairs of nodes you can have on the network. So this is what we did, what we proposed last year in that paper that I advertised at the beginning of the presentation. So you start again with a network G with n nodes, m links, and a clustering method A. You derive the input partitions by applying that method n p times. So this is all the same as before. You construct a consensus matrix, but this time, instead of considering all pairs of nodes, you consider only the pairs of nodes which are neighbors in the original graph. So you only sample basically the consensus clustering, the consensus matrix only based on that. So basically that gives you a matrix which has the same number of elements. Well, actually, you cannot have more elements than the original adjacency matrix of your network, because some of these elements may be 0, because some of these neighbors may never be co-classified. You still do thresholding, just like in the case before. You just set to 0 all the elements below a certain threshold. We show that also in this case, even though we have a sparse matrix already, that this procedure helps basically to get rid of the pairs of nodes which are just weakly co-clustered. And then we add an additional step. It seems to be helping if you use specific algorithm to find your a partition, which consists of closing triads. So basically we add m additional entries. M is just a number of edges, so it's not really parameters, because we found that that's enough to improve the results significantly. Once you have the consensus matrix that you get before, which is sparse, you add an additional up to m additional entries by closing triads. So if you have a triad there in the consensus matrix, you just close it by computing the frequency of co-clustering of the two nodes that close the triads. And yeah, and then you do let me do this. How is I promise to? What happens if I do this? Okay, but then you don't see me. Let me see. Show active speaker video. Yeah, item. Yeah. Okay, so I can put it any height. Right, I can put it here. Sorry about that. So, so now you have your consensus matrix, and you do the same thing as before. You apply your clustering method, the same one that you used at the beginning, again on this new matrix. You get another MP partition, and you repeat the cycle. So the procedure is the same. The only thing is we just sample the consensus matrix to make it sparser, and therefore to kill the complexity of the procedure, which could become heavy. Sorry. Heavy if you do it, you know, if you just do it the old way, basically by sampling the full consensus matrix, by computing the full consensus matrix. So the question is that this is a more noisy procedure than the original one. It doesn't generally converge to a single matrix, to a single set of partitions. So basically to a block diagonal consensus matrix at the end. And you don't even want to wait very long for convergence, because otherwise all the time that you saved by sparsifying the consensus matrix basically is lost by waiting too long to get the result. So what we did is to introduce a stopping criterion for this procedure. And what we did is this. So our stopping criterion is that the convergence, you reach convergence, so you stop the procedure when you finally get a consensus matrix that has less than 2% of entries which are neither 0 nor 1. Because usually have 1, at the end you expect to have only 1s and 0s, which basically means if you get to a partition consensus matrix which has only entries which are 1s and 0s, it means basically that all partitions are identical. It's the same thing. So two nodes are either always co-cluster or never co-cluster, which is exactly the same thing as saying that the partitions are identical. So you never get to the situation here, but as long as you have a few elements which are different from 1s and 0, you can stop the procedure and see what happens. And instead of, that also means that the partition that you get at the end is not only one, you can have, again, MP different partitions, but they are very similar to each other, as I'm going to show next, much more similar to each other than the original partitions. So then, I mean, this choice of 2% looks arbitrary. In many ways it is, but we found that it's a good compromise between trying to have sufficiently stable partitions at the end and not waste too much time waiting for convergence. In fact, we found that if you take any value between 2% and 10% of the elements as a stopping criterion, the results are essentially the same. But if you take 10%, it's still, you accept more noise in your results. So we try to reduce the noise at the same time, guarantee convergence. So for instance, if you take 1%, you get pretty much the same result, but it takes longer to converge. So it's a trade-off. But overall, it's not the proper parameter because the results are fairly much the same. Really depends, if you want to invest more in precisions and less, in saving computer time or vice versa. So let me show you why it's important to have triadic closure, which seems annoying. It's a detail that you didn't have in the original procedure, but this is the reason why eventually we did that. This is a Louvain algorithm. So this is the technique that you're using to derive the initial partitions and all the other partitions every time we apply it on the matrix. This is the normalized mutual information. This is again a test on our benchmark, so you know what the clusters are. And this is the number of additional edges that you're introducing in the system to close the triads. So you see that, so these two lines indicate what is the NMI, so basically the similarity between the partition found by the original algorithm on the network, on our benchmark, and the natural partition of the benchmark, whereas the magenta line here indicates the value of the NMI of the similarity if you apply the full consensus procedure I told you before. So here you see that, and the blue line instead is how the performance of the fast procedure I told you varies if you close these triads. So you see, if you close at the beginning, actually it's not great for this specific method. In fact, it's even worse than the original one. But if you add the triads, if you start to close the triads to, you know, the way I told you, you take a point, you check its neighbors, and if the two neighbors have a zero element of the consensus matrix, you then compute how many times these two nodes have been co-clustered, and you add another entry to your consensus matrix. If you do that, after about m additions, you see that basically the performance is stabilizes, so you don't need to add more than m new elements to the consensus matrix by doing this triadic closure operation, and the final result is better than even the original slow consensus procedure. So this is why we do this triadic closure thing. If you didn't do triadic closure, if you use the Louvain algorithm, which is super fast, it has a lot of issues, but it is very fast. You can actually even underperform the original application of the algorithm on the data. So this tells you basically how stable the partitions are if you, before you apply the procedure and after you apply the procedure. So this brown line indicates the similarity between any two partitions that, in this case, the Louvain algorithm finds for different values of mu in our benchmarks. So you take mu, so you have basically a set of benchmarks, you find a bunch of partitions, usually 20 partitions, you compute the pairwise similarity, you take any pair of partition, you compute the mutual information, in this case, normalized mutual information between any two of them, and then you average, and that gives you the brown line. And then you do our fast consensus clustering procedure, you get the output partitions of this procedure, and you do exactly the same thing. And you see actually that in this case, even after you get past the threshold of mu, after which clusters are undetectable, because basically they are so mixed with each other that there is no community structure anymore, the output partition of the consensus clustering procedure is pretty much consistent with each other, just because it's designed to give you an homogeneous result. Of course, it's a random result, and which you can verify in other ways, but they are very homogeneous. And these are the results that you get now. So now basically you see 3 lines instead of 2 when you really consider the performance of 3 different methods. This is a Clausen-Newman-Moore method. That method was giving those crappy results that you may remember. This is the fast Louvain method, and this is a label propagation. So then you can use different clustering algorithms. If you have other ideas, you can change the clustering algorithm, do the exactly the same thing, because this procedure that I introduced is really independent of the specific clustering technique that you find. Of course, we couldn't test them all. For this paper, we just tested these 3. And in fact, we also tested InfoMap, but the results are not shown. So you see that basically the blue line, which is the one of the consensus clustering procedure, is either the same as the red line. There is an exception in the case of the Clausen-Newman-Moore. Like I say, it's a method nobody really uses anymore. However, remember that now this thing runs much faster, and I'm going to go to that next, than the original consensus technique. But you still see that there is a big gap between the quality of the partition that you find with our consensus clustering procedure and the ones that you can get by applying directly the algorithm without averaging the partition. Especially if you go to larger network size. This is 1,000 nodes, this is 10,000 nodes. And you see actually in this case, the performance is really poor of the original method. The performance of consensus of the fast consensus is similar in this area to the one of full consensus, but it's definitely way better than this very poor performance that you get from the original application. Whereas in the other cases, the performance is still pretty much the same as the one of the much lower initial clustering consensus clustering procedure. Okay, this is just a way that, a plot that we added just to show that with this fast consensus procedure, now we can really take large networks. This is just for example, but it runs really in a very short time. This is a network with 100,000 nodes and 1 million links. And for this one, we can get the performance diagram that you see. And you see actually that with the procedure, with our fast consensus procedure, we can get better than the original one, because the performance dies out later. But with the full consensus procedure, it would be impossible. It will not be possible to get these results in a short time. Excuse me. And this is a diagram that shows, the difference between the complexity of the full procedure, which is this magenta line, and the fast consensus clustering procedure that I just introduced. So the complexity is approximately power, as a power law, dependence on the number of nodes, which is n. It's close to quadratic in the case of the original procedure, and is basically linear in the case of the fast clustering procedure, that consensus clustering procedure that I mentioned. I want to emphasize that this 1.2 instead of 1 is because of the implementation we use for Louvain, which should be linear, which for some reasons is a little bit super linear, because by default, by the way, we implement our fast consensus clustering techniques, the procedure itself is linear. So that most of the time is spent in applying the clustering algorithm on the network, and after that on the consensus matrix to get the result. So you see here how far we can go. We can go up to 1 million nodes, which will be completely unreachable by this one. This is actually the reason why we did that, to get pretty much the same results and better results than the direct application of the methods or the clustering method of your choice on the data at a much lower price, computational price. Okay. So I don't know how much time I have. Alessia, could you tell me?
Well, actually, a few minutes, perhaps, if we want to leave.
Sure. A couple of minutes. Okay, then
about 5 minutes, right?
Yeah. Okay, so let me skip this part, which was about showing that you can apply consensus clustering not necessarily on a static graph. You can use it also for dynamic graph, basically to put together partitions that you find at different time snapshots of your system. And I gave a couple of examples. So let me go directly to the conclusion, because I would like to advertise a couple of things. So the basic message is that there is noise when you apply any clustering, most clustering methods, most clustering techniques on any network. So how to deal with noise? The easiest thing, it would be just to pick the partition which appears to be best according to the optimization procedure, optimization criterion that you're following, because most clustering techniques are based on the optimization of some function. But I showed you that you can do better by using also the suboptimal partition, by combining them in a consensus matrix and clustering the consensus matrix instead. And what I showed you today is that the original technique could have bad complexity that could approach quadratic if you're unlucky and you have some big clusters in your partition, big somehow of a size comparable to the size of the whole system. But it is possible to do much better by creating a consensus matrix which is sampled, just considering the scores on pairs of neighbors instead of any two nodes. This brings down the complexity to linear for the fast consensus procedure. And basically, in that case, the actual complexity of the full routine is the complexity of the clustering technique that you're using. So nowadays, there are techniques which are basically linear, and that allows you to analyze networks with millions, tens of millions of nodes. If you use one of those techniques, also this fast consensus clustering procedure is going to be linear. So because it's the way you construct the consensus matrix is linear, everything else is linear. So this is a way to save time and to be able to apply this technique on very large networks. Okay, sorry. The code is actually in this GitHub. We are just actually turning it from network X to iGraph because it's much faster that way. So if you use the one which is already there, it's not going to be so impressive. I mean, we're going to put soon in GitHub a faster version of that. I mean, it's the same algorithm just implemented in iGraph using iGraph libraries. Just let me make sure that you get the take-home message because you're going to forget the details. So you don't have to expect miracles from this technique. You know, it's not like a God-given thing because it also depends on the quality of the input partitions, because what it does is some sort of average of those partitions. So there are three different scenarios that you may face in this situation. If the input partitions are very similar to each other, the technique also returns very similar partitions. It's like when you average numbers which are very close to each other, right? Then you can almost take any one of them. So you don't gain much by doing that. If the partitions are very different, then you can expect something intermediate which has no meaning. And there are actually now recent work, discussions about, I mean, you can get different partitions just because there are different solutions. You know, like for instance, you may have a hierarchical structure, then you have partitions with big blocks, partitions with small blocks, and both of them, and all of them are significant. But it may also mean that basically there is no community structure, just because you get different things. It's like getting a random partition every time. The best domain, best regime where consensus clustering is most likely to give you a result is the one in which you have some variability in the input partition, but not too much. And what that means, I mean, it's just can be quantified, but I just leave it like this for you to remember. So just let me quickly remind you that for those of you who are not familiar with graph clustering, I recommend you to read my original survey, which is like 100 pages, a big one. I'm actually writing a book now. I mean, I've been working on it for years. Hopefully next year I will finish, which is much bigger than that, because of course, after 10 years, there are many things here which are obsolete, but there are also many popular algorithms that people are using today, which are described in the original review. I did a more recent review more lately. This is actually one of the best known, most cited papers in network science. More recently, I published another review with my former student, colleagues, which is supposed to be more on the principles and less on the description of the algorithm and where we are, after some years, where we are going, more like, in this direction. So in this respect, is complementary to the other one and more, of course, up to date. And the last couple of things I want to say, we published a book that came out at the beginning of this year, a first course in network science, a textbook in this discipline, which is supposed to be the most accessible textbook in network science. It's really undergraduate level. It's for our undergraduate students. It's an hands-on approach. We have a lot of exercises, also a lot of code exercises in Python. So we also teach how to program in Python if you do that. The approach is software-based and it's based on network X, using a network X libraries because network X library, because it has a lot of built-in functions which just compute directly a lot of things which have to do with networks. But in general, you can also then move to different platforms after that. At least, I also learned Python this way. I was a very old-fashioned Fortran programmer before then. We also make available the solutions to all exercises, including the one in code. So we also give you the notebook, so you don't even have to solve these things on your own. If you want to give this exercise to your students, if you are an instructor and you buy the book, you can have access to the solutions and to a complete set of slides, both in PowerPoint and in Keynote, which basically have all the contents of the course, all the figures of the course from the beginning to the end. So this is really meant to be for people who do not have, students who do not have a strong technical background. There is very, very little math, few formulas included in gray boxes that you can skip without sacrificing the understanding. And I hope you're gonna like that. And there are also free tutorials that you can perhaps also go through at any time. You find them on GitHub, one for each chapter. This is, for instance, the one of chapter 7, which is the last chapter of the book, and the one about dynamics on networks. And this is, for instance, a part about the SIS model, since we're talking about epidemic spreading a lot in this year. So you can also see how we can implement it. And last couple of advertisements, we are organizing Networks 2021, which is possibly the largest ever meeting in network, because it's a merger of Sunbelt, the Sunbelt Conference and NetSci Conference. supposed to be next July in Washington. We're working on a hybrid model because we don't know if we are still out of the woods next summer, if people can travel, So we are preparing something which is partly online and partly in person. We may have to switch it to online only at some point if we see that, we're still in the best situation. But I encourage everybody to participate because this is going to be really, it's a unique event. So it's probably going to have the largest number ever attendees of any network meeting so far. And finally, I want to, focus your attention on this program supported by the NSF, National Science Foundation here in the States, which is the first international mobility program between the US and Europe about the topic of multi-layer network science. So in fact, the bulk of the program is, and most of the money, that almost $2 million basically for this program, consists in supporting sponsoring visits of researchers, young researchers, postdocs, young faculty, PhD student from the US to Europe to work with somebody on multi-layer network science. For obvious reasons, because of COVID, we cannot have mobility right now. We have to start the program, but we're organizing event. We have a webinar series. This is actually a snapshot of the website. These are the main people involved. I'm a PI of this program together with Alessandro Vespignani, and people at the bottom are the 4 representatives of 4 European institutions, but they are not the only ones. This is an inclusive program. We have a big mailing list. If you're interested in this topic, if you work on multi-level network science, you can join, you can get our updates, be involved in many different ways. And with that, I'm ready to take your questions if you have any. Thank you.
And thank you, Santo. Yes, and the floor is open for questions and comments.
Hey, may I ask a question?
Yeah, sure.
Okay.
Thank you very much for your talk. I have basically 2 questions. So first of all, you talked about improvement and approximation of your own methods for consensus-based clustering, but my question may be relevant to modern advances in network science related to graph embeddings and the existence of models that now take into account cluster structure and could build graph embedding together with community structure, leading to very simple application in which clustering is made based on k-means or dbScan in embedding space. Could you shed the light what's the future of such methods, and can the current community detection methods can be incorporated in graph embedding based models? And
this is,
second,
yeah. Oh, sorry. Okay, so I'll let you ask the second question.
Okay,
anyway,
and the second question is regarding the last slides about mobility and so on. So basically, people in Russia are very interested in the question whether there will be open remote opportunities to collaborate. Because as you know, it's like many people are not ready to go on kind of PhD postdoc positions if they already has some kind of job right now. But people are waiting for open and remote positions for collaboration, because I consider for the past half a year, everybody know how to use Zoom, Overleaf, and so on to work together. And that's my second question. So your opinion and the current situation, what's going on? Thank you very much.
Thanks a lot. I mean, these are really great questions. I mean, I don't know how much time we have, but this really could be a long discussion. So, but to your first, the technical one about the talk, this is a great question. It's the same question that I asked myself last year. We just published a paper, actually published, we put it online. So I can send you the reference to that if you give me your email, or perhaps I can also put it in the Zoom chat for everyone to share. Just about that. I mean, do we gain anything if you use, I don't know, not to vec, deep walk, or these very recent graph embedding techniques, and then turn the problem from a graph clustering problem into a data clustering problem using, like you said, dbScan, k-means, and so on? So the answer is no. I mean, meaning that these methods seem to underperform some of those that I mentioned before, which are even non-parametric, whereas, as you know, not to vec has 7 parameters, deep walk has 5 parameters, so there are things. So just because, but we published the work because I was personally curious. I would say, oh, maybe now finally we can, we can simplify things, which does not mean that the idea is wrong. It means that I ended the conclusion part of that paper by encouraging people like you who are familiar with these things, the deep learning techniques and so on, to create new embeddings which are focused on modular structure. So, I mean, of course, random walk is also one way. I mean, the info map that I mentioned before is based on random walk and is very effective, at least on our benchmark. And we use our benchmark, which of course does not mean that this is the universe, But I mean, the performance can get to levels which are comparable, but it really strongly depends on the choice of the parameters. And we couldn't find a single set of parameters. Actually, I would have loved to say, look, I mean, if you want to apply not to back instead, and then of course use k-means afterwards, then you can use this set of parameters instead of the ones that are recommended by the developer for, I don't know, no classifications or link prediction. And we couldn't do that because depending on the value of mu, this level of embed of mixture between the classes, we will find that the optimal set of parameters was really changing considerably. And on top of that, and that's a more general question, and could be actually undermining this whole thing. Consider that k-means is a quadratic complexity most of the time. So even if you can get a very good separation of the data points, you may also lose your edge. And of course, not2vec can do it very fast, and all these techniques are super fast in doing the embedding. But the embedding is not the end of it. After the embedding, you have to separate the points. And right now, the best techniques to separate points in space are, I don't know, you just go to classic ones, they are super linear. And the current world we live in, if you want to analyze networks with millions and millions of nodes, you want to separate them in a reasonably short time before you finish your PhD specifically, you should really go to linear complexity. So if you do science which is super fast to do embedding, a science which is super slow to do the separation, it's not a good trade-off. So this is where we are now. And I'm more than happy to share with you the link to the archive paper, which is still under review for PRE, that basically, summarizes the results of this analysis. The second question, of course, is more political, somehow about the situation. It's true, we're learning to live in this virtual world. Actually, I'm just sitting on my dining table. You see also this is actually one of the pictures of our book. So, and we're getting used to that in a sense. It incentivizes collaboration. We're getting used to that. Specifically, our program, you can subscribe to the program. You can add your name to the mailing list. It's open to everybody if you're interested. It's more, we couldn't do something for the whole of network science because instead of 2 million, we would have needed like $20 million for that because it's so big. So we had to focus a little bit, and we decided to focus on multi-layer network science because in the last few years, this is a big paradigm. A lot of people are working on that from different disciplines. So we focused on this one. So if you have any interest in that, or if you plan at some point, not necessarily your main interest, if this is one of the things that you like to do or to explore at some point, just subscribe to our mailing list and you get updates. We have an initial set of partners that are supposed to exchange research personnel, and most of the money of the grant goes in supporting the travel and to give them a stipend to pay their bills. When you move to the state for a few months, it's usually a semester. The idea was a semester long exchange, so that you can create this dense network of collaboration, but in principle, everybody's invited. And you also live in Europe. So and then specifically, if you mention, I don't know, the potential of collaborating with me or with some of the great people we have here, we can also have separate conversation on that. You can tell me what you do and so on. Are you a PhD student?
I'm currently a very late PhD student at University of Ljubljana on graph embedding and the application of learning on graphs, but basically I'm mostly a researcher at High School of Economics here and several other research institutes. So just an interesting question, because again, we are sitting at home and what can be done is like we're researchers and we're researching.
Yeah, we should really search for each other.
Table, with full blocks visualization behind you. So it's quite interesting to see the experience. Thank you very much for answering the question.
Thanks to you.
Okay, colleagues, although officially we're supposed to finish, but because we started later, I think we have a full right for a few more questions.
Santo, I have one question. May I ask you?
Oh, sure. Nice to see you, Sergey.
Nice to see you. Thank you. First of all, thank you for your presentation. My question is following. Do you think about the application of deformant entropy of just the information measure to get the correct number of parameters mu? For example, you transform your frequency into probability, and then you can calculate, just go through the matrix, you can calculate the information weight of current solution. And if you change the mu as a parameter, as a deformation parameter of such entropy, then you can get the good results just to choose these parameters. For example, we had the same situation in topic modeling. We had the problem with the numbers of the topics, which is influenced as a parameter for deformations. Do you think in the direction of the deformant entropy?
You know what? This is a great idea. So you expect to get an email from me one of these days. Somehow we talk this through. I'm thinking this is really very prime. I mean, just in general, the idea that, of course, I mean, obviously, this probability depends on the method that you're applying. But if you have a sufficiently high number of partitions, then you can really interpret it as a probability that two nodes end up in the same cluster, which is in a sense the whole principle of this approach. And right. So basically, you can compute the entropy of that ensemble of partition, and as a function of mu, you can also see if there is, because it's a smoother function instead of applying again a cluster, a technique and so on. This is a great idea. I'll look into that. So, and of course, in this case, since it comes from you, if you're gonna do anything about that, you're gonna be involved. Thank you.
Okay, I can write in email to you just to explain
Sure.
my idea.
Please do that. And if
Okay.
you have a reference to what is it, like LDA? I don't know if we're referring to that when you mentioned topic modeling.
Yeah, it's already published in several conferences, so I just give the reference.
Yeah, please. Thanks. I mean, I'm really interested in that. I mean, potentially. I mean, right now it looks like a great idea, but of course I need some time to process it.
Yeah, okay. Thank you.
Thank you. I think we can take one more question. Okay. If there are no more questions, I think we should thank Santo Fortunato for this most interesting talk this Friday evening. And thank you everybody for staying.
Yeah, thanks a lot. Thanks. Okay, I don't know how it works in online things. Thanks a lot, guys. See you soon.
See you.
Yeah.
Thank you.
Thank you very much, Santo,
Yeah,
for
thank you.
accepting the invitation.
Sure.
I like these topics very much, both the clustering of graphs, social networks, and consensus clustering.
Yeah. Thanks for reaching out, the way you did. So I almost forgot about this because it was like in the spring, when we were in isolation.
Yeah.
Contact. So, but I was happy that I could do it this time.
Yeah, but we suddenly popped up.
Yeah, right. We suddenly popped up.
Thank you.
Thanks a lot, guys. Hold on, and we get out of this one day. See you.
Yeah, hopefully.
Bye.
See you.